Okay, so now we will try to understand the algorithm that we have just seen using, you know, a practical example, you can say. Not example, to some extent you can say a use case. Say for example, you have a situation like this. You have a data set having two features. Okay. And you have a and that data set also have output of two features. Okay. You want to implement a multi-layer perceptron for learning that data set. So how the MLP will look like? The MLP will look like this, you see. So you will have two features. So that's why two neurons in the input layer and there is a bias. Similarly, you will have some set of, say for example, three neurons in the hidden layer and obviously another bias, and you will have only two neurons in the output layer, right? Try to understand the connections. Each and every neuron is connected with other neurons by individual connections, you see. Even the bias also connected with all the neurons in the next layer that I just told you in previously, right? So just to differentiate a bias with a neuron, I have changed the color here. So since it is biased, that's why there is no input. It's considered as +1 always. Now, how the bias will impact in this learning, that will be decided by the weight values by which this bias is connected with the other neurons in the next layer. For example, 0.23, 0.11, 0.27 are the weight of the connections between the bias of input layer with the neurons of the output of the hidden layer. Similarly, 0.03, 0.19 is the weight of the connections between the bias of the hidden layer with the neuron of the output layer. Always remember that bias of one layer is not connected with bias of another layer. It's not like that. Okay. So assume we passed some input to this input layer. We have some arbitrary connection weights. As I told you, some random weights. We start with random weights for both all these weights between input to hidden or hidden to output layer. And maybe assume that because of these weights, I'm not going to calculate rigorously what will be the output from this output layer. I mean, sorry, hidden layer and all. Assume that output layer gives an output 0.35 from this neuron, first output neuron, and the desired is say 0.99. Okay. And from this neuron, it gives output 0.52, where desired is 0.01. So naturally, from both of this uh, output neuron will have some error, and that we have calculated here. E1 equal to 0.64 means 0.99 minus 0.35, which is 0.64. E2 equal to 0.52 minus 0.01, that is 0.51. So once we calculate this, our you know our you can say the backpropagation will start. But before that, one more thing you should very clear in your mind, that is how these weights are represented within the programming. It can be something like this, you see. So it looks something like this. The same thing I have written. This is the situation, and I am now trying to show you the the representation of the weights from the programming point of view. Say we have two inputs, so the pattern vector should look something like this: x1, x2 bias. for one data point. This is for one data point. X1 value is 0.20 as it is given here. X2 is 0.75 as given here. And bias is always +1 as we all know. Now, how we will represent these weights between input to hidden and hidden to output layer? We can do that by a matrix. Because ultimately what we have to do? We have to multiply these weights with the, each and every input of the, each and every neuron input. For example, I have to multiply these x's with w to get the output here, to get the summer value here. So it is always better if we do it parallelly, right? Now, for doing this parallelly, the best way is to consider a matrix calculation, because in case of matrix calculation is done parallelly. How? Let's see. First of all, you see it's given, the weight matrix is given like this, 3 cross 3 and like this. Now, what will be the dimension? The dimension can be represented by, you can say for example, you can say the, if you have ith, if you want to connect, if you want to create a weight matrix between the ith layer to jth layer, the dimension of the weight matrix should be j cross I. Sorry, not j cross I, it should be j cross I plus 1. Why I am saying? Because assume this is ith layer and this is jth layer. How many neurons are there in jth layer? Don't consider bias. Bias is not a neuron. Neuron is number of neuron is 3. So in jth layer we have 3 neurons, and in ith layer I have 2 neurons. So the weight matrix can be represented by 3 cross 2 plus 1. This 2 plus 1. Why I am considering plus 1? Because I will basically calculate the weight between the bias also. That's why I am saying 3 cross 2 plus 1. That means that's why 3 cross 3 is given. So just check it. 0.75 is this one. Then 0.45 is this one. That means this one. So, by row it is representing, by column it is representing these neurons. So this column, the first column is representing first neuron. The second column is the second neuron. Second neuron means connection between the weights of the second neuron with the weights, with the other neurons of the next layer. See, 0.90 is here. This neuron with this one, 0.14. This neuron with this one, this is 0.14. 0.32. This neuron with this one, 0.32. Like this. Similarly, if you look into the second set, that means this set of weights, again apply the same logic. I number of neurons here and j number of neurons here. The weight matrix will be j cross I plus 1. That's why 2 cross I means 3, 3 plus 1, 4. Because of this bias. That's why it is 2 cross 4. So if you remember in this way, it will be easier to, start writing code. Now, you may have in your own version, own representation. Obviously, that's always welcome. But if you want to represent efficiently with some matrix form, maybe it will be a very good option. So this is the weight matrix. This is the input, and output will be represented again in some form of vector. So the output, that 0.35 and 0.52 will look something like this. A column vector. Because of this output will have some error. So this error is again some column vector. 0.64 and 0.51. Right? So now if we go for forward pass, what's happening in the forward pass? In the forward pass, you see what's happening. These, first of all, just try to understand. These are the thing that we have. But how we are getting? We are getting, first of all, we are calculating the hidden layer output, right? We have to calculate. Hidden layer output means output from these layers, right? How to do that? Obviously, this V1, V2, V3, these are the outputs. I mean, summer value, you can say. The summer value is what? Weight multiplied by the inputs. So these are the weights multiplied by inputs. This is the input. Okay. So weight multiplied by input. This one. Now what we are doing? We are applying some sigmoid function over this summer value. Then you are getting output, right? So if we apply sigmoid function individually on this three values, we will get y1, y2, y3. We will have some values here. If you calculate it, you will see maybe you will have some values like this. So you see you got the output of three neurons present in the hidden layer as 0.742, 0.576, 0.6. Since the calculation, we have done this calculation by matrix multiplication, that's why it becomes parallel. Otherwise, you have to write for loop, which is definitely an inefficient compared to matrix calculation. That's why matrix is very, very vital here. Anyway, so once we calculate the output of the hidden layer neuron, now we have to go for the next pass. I mean, from hidden to output layer. That is not yet done. So you have to do that. So what we will do? Now we will basically do this weight into the output. But here, this is the output of only 3 neurons. But we have one more bias also. That means when we will try to find the output of from the output layer, I mean, we have to compute, we have to basically, what we have to do, we have to multiply the weight of this into the output from here, 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 as well as here. But this is a bias, it does not have any output. So its output always considered as +1, right? So that's why you see it is given as +1 written. So this particular weight matrix is always obvious, I mean already there. The it's 2 cross 4 matrix and it's 4 cross 1. So 2 cross 4 multiplied by 4 cross 1. So it becomes 2 cross 1 matrix, right? So automatically you will get a 2 cross 1 vector, column vector, on which if you again apply some sigmoid function, you will get some output again. Now this output is from the output layer neurons. So the output layer neuron got 0.663 and 0.690 as an output, right? Once you get these outputs, you can start calculating the errors. What you can do, you can check these errors by 0.99, 0.01. This was your desired value, already you have seen, and this is what you have just got. So you can simply do the, simply do the subtraction between these two column vector and get the column vector having error value. Now, I've not basically calculated the, rigorously I have shown the calculation of the delta, but the delta can be again calculated by this matrix form, because if you look into the delta part, what was the equation of delta k? The delta k was something like this. That means delta 1 equal to error 1 into phi of vk, means phi of v1. That means into 1 minus phi of v1. Right? delta 2 equal to E2 phi of V2 into 1 minus phi of V2. So it's very straightforward. So if you put this delta 1, delta 2, delta 3 as a column vector, then all this E1 into phi E1, E2, E3, phi of V1, 1 minus phi of V1, then phi of V2, 1 minus phi of V2 will be, can be stored in as a column. So what will happen? We can simply put these as a column vector. So that is what actually given here. You see, if you look into this delta calculation part, it is given just by this calculation. So that means you see here that the delta 1 and delta 2 we have actually calculated parallelly by this simple matrix calculation. So we have got these deltas of output layer. Now using this delta we can calculate the delta of hidden layer. But interestingly, you see, I have done simple matrix calculation. Just like, that's why sometimes I needed to do some transpose of the matrix just to, keep the dimension properly so that you can do the proper multiplication. If you want to go for matrix multiplication, your dimension should match. Just to match the dimension, we had to do this transpose operations. That you have to understand, right? So anyway, so I'm not going in much detail on this. I hope it is clear to you that how you are basically calculating the deltas, because the delta calculation is basically very straightforward. Okay, just instead of doing the delta 1 delta 2 individually, we are applying some matrix rule so that at a time all the delta is calculated, which saves the time, right? So now once this delta is calculated, now it's become very easy, right? Because we have to find the delta W. Delta W of, hidden to output layer weight and also input to hidden layer weight. But delta W, once this delta of hidden layer and delta of output layer is calculated, then you can simply go back to by the equation, right? Here, delta W Kj equal to eta multiplied by delta K multiplied by Yj. So if you see here, it's nothing but delta multiplied by Y is this, right? So you are getting this W since it is transposed. So one, it's 2 cross 1 and it become 1 cross 4. So 2 cross 4, and which is required because your W for hidden to output layer weight was dimension of 2 cross 4. So definitely your delta W has to be 2 cross 4. Otherwise you cannot do the addition of W plus delta W that you have got. Similarly, you can get delta W between input to hidden layer weight by the same rule, delta into the outputs, right? So once you get this deltas, you can simply add them, right? This was your initial weight, this was your delta. If you add them, we will get the new W. Similarly, this was your initial weight, this was your delta. You will get a new set of W. And that new set of W, that means with respect to architecture, if you see what was your 0.75, it will become 0.753. What is your 0.045, sorry, 0.45 will become 0.449. It was 0.12, it becomes 0.98. So in this way, the weights are adjusted. Now this is, I have just shown you only one forward pass and the corresponding back propagation. But once the new weight come, what will happen? Another set of input will be forwarded, another set of error will come, and again those calculations will be applied, and then again some weights will be adjusted. and in this way we can carry on these things. Either until you complete all the data set, all the pattern of the data, or you can say you can repeat all the patterns, and until and unless you are getting some error which is very less than some threshold value. Okay, so this is what an example we have seen to continue learning of multi-layer perceptron. Now what we can do, we can try to implement this in a Python code, right? So let's do one thing, let's implement this in a Python code by using some example dataset.